I want to report some joint work with Tomauka from the University of Tübingen. Okay. We were discussing quantum statistical mechanics, foundations of quantum mechanics, errors of time. Last year, we realized there is interesting phenomena. We didn't have a name for it back then. Now we call this observation typicality. That was surprisingly strong, and yet nobody had discovered this before. But it was based on existing results that have been known for over a decade in the field of thermodynamics and quantum information theory and quantum mechanics. So I want to share some of the work today with you guys. And I want to focus on the core part, the conceptual part, but there's some mathematical scaffolding to build up to it. So feel free to ask clarification questions during the talk, and you can save the substantive questions to Q&A. Okay. The universe and its parts are quantum systems. After a century, there's still a deep puzzle. What does quantum theory say about physical reality? Is it a field, a bunch of particles? What is it? At the heart of quantum theory is something called the quantum state. We've seen various names. Familiar one is the wave function, a vector in Hilbert space. There was more abstract things called density matrices in Hilbert space. But regardless, we want to learn to know what a quantum state is, right? And to learn what quantum state is, we perform various measurements and observe their outcomes. Why do you want to learn the quantum state? Well, it's similar in any kind of physical theory. The state gives a lot of information about things you can observe and things you can test in the future, is to enable better predictions, for one thing, scientific goals, but also to understand what's going on in the system. But one crucial difference here is that, reminder, quantum predictions are paradigmatically somewhat chancy, probabilistic, stochastic, and those probabilities are in accord with the Bohr rule of probability in quantum mechanics, and called psi-mod square measure of the wave function. And there are lots of research programs in quantum information, quantum tomography, quantum computing, trying to sharpen how we get information about the quantum state from measurements, and then how to make predictions in the future. Okay. Now, we know that quantum learning is difficult. To learn what a quantum state is not so easy. But is it at least possible? Well, of course, we learn in quantum mechanics textbooks. For spin experiment, for a stern field experiment, you get information about quantum state. They're small systems. But the new finding is that no, not even in principle, if the system is large enough. Hold on. Projector is oh, okay, it's back. All right. Okay. The new finding is that no, it's not. Quantum learning, quantum system is not even possible, not even in principle, if the system is large enough, unless we already know what a quantum state is, which we don't need to learn what it is, right? If you know what a quantum state is, that's fine. If a physical law tells you what the quantum state is, that's fine too. But if a physical law says it is one of those, but I don't tell you which, right? And only learn what a quantum state is by doing measurements and observations. Is that even possible? For small systems, yes, but for large systems, no. So what are we learning in the quantum universe? The quantum universe is pretty large, have many degrees of freedom. The quantum state is a quantum state of a large system. Not the quantum state, but nearly entirely about something else. This inverse relation between the quantum state and additional ontologies, which we tease out in the epistemology of quantum theory. Okay, so our project doing with Tomauka here, pertains to limitations to knowledge, typicality theorems in quantum physical mechanics, wave function realism, density matrix realism debate in quantum foundations. And the very surprising discovery about quantum theory is what we call observation typicality. Okay, so explain what this means and give you some background to warm up to it and explore the epistemological implications of this result. In classical mechanics, observations can tell you a lot. observations can, oh, sorry. Is the projector working okay? Okay, let me try again. Okay, this works. And maybe just leave this not full screen and see how it works. Okay? Maybe the full screen not option. Maybe the full screen thing has some kind of bug. Okay. Maybe let's leave this as paused. Okay. All right. Okay. So in classical mechanics, we can learn a lot about the classical state. Observations can distinguish among typical phase points in phase space. For example, a classical point toss experiment with two possible outcomes, tails and heads for the point. And if you observe the tails outcome, this rules out half the points in the initial phase space. So it can distinguish phase points. Such observations can provide reliable information about the actual state of the system. The classical learning is possible. Learning about classical state in a small and large system is possible. You can do updating, you can classification and so on. You can just learn what the state is more and more by narrowing down possibilities. Just like if you have possible word semantics, you start with the most spread out kind of state, and then you kind of increase knowledge by contracting the space of possibilities down to something narrower and narrower. Now, in quantum mechanics, the surprising discovery is that observations cannot distinguish among typical wave functions in any high-dimensional Hilbert space. So the Hilbert space here is analog of phase space in classical mechanics. The space of possible wave functions, possible quantum states. You can learn what is the quantum state, the actual world, where observation cannot distinguish among wave function and high-dimensional Hilbert space if it is a typical wave function. So in a sense, quantum learning is in principle impossible. I'll make this sense precise later with different corollaries and theorems. So roughly speaking, our new result is this. In any high-dimensional Hilbert space, so a state space of possibilities that's large enough, typical universal quantum states are observationally indistinguishable. The two classes of results. First, no observation can reliably distinguish typical universal quantum states. So universal quantum states are quantum states of the whole universe. They can also be quantum states of a large system that includes us. Second, no observation can even unreliably distinguish typical universal quantum states, provided it is not too improbable. If the observation itself is not too unlikely, it's not too small probability, then no observation can even unreliably give you information about quantum state. Say in the Bayesian sense, or in other kind of favoring likelihood sense. We call this fact observation typicality. Observation typicality is the strongest known result about the limitation to knowledge in the quantum universe. Dewar, Goldstein, and Zanke proved already that it is impossible to measure a wave function precisely. Think about a delta function peaked around some particular point. That is impossible just because there's no POVM corresponding to that delta function. Our result goes one step in this direction, but goes further. Even an imprecise measurement is impossible. No observation would give us any substantive information about the quantum state of a big system, including that of the system, universe. So even narrowing down significantly is impossible. You can kind of if you think about David Lewis' sense of information gathering, information state propositions as sets of worlds, you cannot go from a big set to a small set in quantum theory. There's no such learning as possible. So nature, if it is quantum, is more secretive than we have realized. Now, here's some motivation for thinking about this result and thinking about application of the typicality theorems in our universe. One might say, of course, our universe is not typical. In one sense, it is not in thermal equilibrium. It is not a soup with no structure at all. We have galaxies and stars and people and cats and dogs. But it is typical in another sense. Given an assumption of past hypothesis of a low entropy initial state, represented by some kind of initial subspace H0, the initial wave function is assumed to be a typical element of this initial subspace H0. Of course, it takes a lot of work to spell out what H0 is, how to define this typicality measure. But just conceptually, what is the role of the past hypothesis? Is to find this atypical kind of subspace among many, many wave functions and say, okay, given this conditional on this subspace, the quantum state of the actual world we believe is typical in this subspace. And this is to explain the widespread error of time in a universe governed by time symmetric dynamical laws. We assume here for this project and for simplicity, but we can of course relax various assumptions later. Just to conceptually, we can assume here that there is a wave function psi t of the universe. So when I give this talk in a physics conference, I have to clarify, defend, and really stick to my ground and say there is a universe. And of course, there's a universe, the state of the universe, and it's a quantum state, and it's a time index. But that can be controversial in the physics setting. But here, I think, makes sense. People understand what I mean by saying there's a universe, and there's a state of the universe, quantum state psi t. Okay. Now, at the initial time t0 of the universe, the initial wave function can lie in a particular subspace H0 of the Hilbert space of the universe. There's the past hypothesis, this various versions by curvature hypothesis. Maybe there's Hartle-Hawken wave function, precise wave function too. Now, if the subspace has enough dimensions, observation typicality asserts that our empirical data at any time t is any data, precise, imprecise, coarse-grained, fine-grained, global, and local. Our empirical data at any time t will reveal very little about psi t0. We quantify how little with precise theorems. So this suggests that typical initial quantum states of the universe are observationally indistinguishable from each other. Now, if there's no collapse of the wave function, there's no kind of collapse with the time evolution is unitary. Also, psi t cannot be distinguished empirically from commutative vectors in the appropriate subspace, evolving into subspace forward in time. And later, quantum states cannot be distinguished empirically either if they're typical. And our result is based on two mathematical facts. One, the main theorem about POVMs is kind of a well-known thing in quantum measurement theory. And second is distribution typicality. It's something that's been proven about 17 years ago and recently rigorously by Tomałka, my collaborator, and his other co-authors, Cornelius Vogel and Stefan Teufel, in the paper last year. And I'll discuss these two results intuitively in the next few slides. Okay. So the main theorem about POVMs are as follows. So POVM stands for positive operator value measure. Generalization, kind of observable, as given by self-adjoint operator. So you can think about POVM as a set of possible measurement outcomes. So in the kind of coarse-grained sense, you can have you have some pointer in some experiment. You have pointer position 1, 2, 3, 4, 5. The probabilities of various outcomes add up to 1, and they have some mathematical properties that make them suitable for doing measurement theory in quantum mechanics. And one can prove this theorem in various interpretation of quantum mechanics, called the main theorem of POVMs. For every quantum physical experiment E on a quantum system S, whose possible outcome lie in some space Z, say a discrete space or a continuous space, there exists a POVM E on Z. So E is going to be a set of operators such that whenever the system has wave function psi at the beginning of experiment E, the random outcome Z has probability given by this Born distribution. So the probability of the Z taking value small z equals to expectation value of EZ. EZ is the element of the POVM representing the outcome Z, small z. That's the Born rule. Okay. Now, that's the first result. That was kind of standard thing that people are familiar with in POVM theory. But the next thing is something perhaps less familiar in philosophy and also maybe less familiar in physics. It is more well-known in quantum statistical mechanics and quantum thermodynamics literature. There are various theorems like this, typicality theorems. There are different flavors, conditions, clauses. But this theorem is particularly elegant, and it's very suitable for this particular result we want to argue for. Okay, so it's based on an elegant but counterintuitive mathematical fact that's been known for at least 18 years, recently proven rigorously. It is an instance of the concentration of measure phenomena in high-dimensional spheres. Okay, so when I gave this talk in New York last time, I didn't have a whiteboard or projector, so I just brought an orange. And you can kind of see this result, roughly speaking, in orange. So suppose I give you an orange in 3 dimensions. I give you only the skin. You say, oh, that's cheating. I want an orange, not a coat of skin. But suppose I give you orange in 100 dimensions and give you the skin. Now the skin 100 dimensions orange contains almost all the mass of the orange. You can see this roughly by thinking about the radius of the orange, power to the power n, give you the volume, right? So you have kind of volume, radius from 0 to 1 interval, that orange in high dimensions. Now, if you chop in two, 1/2 versus 1/2 to 1, right? The first interval, the small sphere, small ball inside in the inner core, contains volume almost close to 0. Why is that? Because 1/2 to the power of 2, 3, 4, 5, 6, 7 gets closer and closer to 0. Okay. It's flickering. Okay. The demo have the handout, by the way. Handout, okay. In case. Is it still on, projector? Oh, okay, it's back on. Every time I mention the nature's secret, nature's kind of shining a light here. Okay. So in high dimensions, the mass of the orange is concentrated around the outer shell. And moreover, if you think about the sphere, just the skin on the outer sphere, right? And the sphere, almost all the area of the sphere is concentrated around the equatorial band, a small band around the equator that contains almost all the area of the orange skin. And moreover, here's another counterintuitive fact. Intersection of two equatorial bands will be a very small kind of thing in the middle, and that still contains almost all the area of the orange sphere. So that's kind of counterintuitive. But from that, you can actually show that in a high-dimensional Hilbert space, because Hilbert space in high dimensions, in the sphere of wave functions, unit sphere, that's like high-dimensional orange. And for the high-dimensional orange, remember the equatorial band contains almost all the mass. Any equatorial band contains almost all the mass. And there's analog of this for the quantum case. That is, for any experimental outcome, most quantum states predicted with nearly identical Born rule probabilities. Okay, so let me give you some terminology and definition. Let S H0 be the unit sphere in subspace H0. So think about this as the high-dimensional orange sphere. And let D0 be the dimension of Hilbert space H0, measure how big the sphere is. And rho 0 be the normalized projection onto H0. Mu0 being the uniform distribution over SH0, which measures the normalized surface area measure. You can, of course, use other bias measures here, but for simplicity, I'm going to use uniform measure. And you can have better generalizations of theorems using bias Gaussian measures. And let's say a sentence about psi. F psi is true for 1 minus epsilon most psi in the unit sphere. When we say that the set S containing, let's say mu of S is greater than 1 minus epsilon. Right. The set of wave functions satisfying the sentence S of psi has the measure that's almost close to 1. Okay. So here's the key theorem we're going to use in our argument. So it's called distribution typicality. Let H0 be an arbitrary subspace with finite dimension D0 in H. So H0 is arbitrary high-dimensional subspace, finite-dimensional subspace, and let the operator EZ be an element of an arbitrary POVM on H. Then for every positive number epsilon, for 1 minus epsilon most wave functions in unit sphere, the Born distribution of EZ given by the wave function psi is different from the ensemble average bounded by this error term, 1 over square root of epsilon times D0. Already you can see this gives a very nice bound if D0 is large and epsilon is not too small, right? So consider epsilon to be 10 to the minus 200. But D0 for the universe, or even for a macroscopic system, can be as big as 10 to the power of 100, right? 10 to the power of something much larger than 100. Then this term on the right will be very close to 0. The distribution typicality is a particular case of a theorem proven by Toyfo and co-authors last year. It can also be derived from the theorem proven by Peter Ryman in 2007. That's why this result has been known for at least since 2007. Okay. And it says that the Born distribution for EZ is close to the average value, provided that right-hand side is small, which will be the case whenever the dimension of the Hilbert space is far larger than 1 over epsilon. So here's the next example. I always do the math wrong because exponentials and powers get very, easy to make mistakes. So here's one example. A macroscopic system with many particles, that's how many? N to the 10 to the 20 particles, is in some macro state mu. The dimension of Hilbert space, H0 of the system, scales exponentially with N. Think about entanglement, right? Let us suppose D0 equals to 10 to the power of 10 to the power of 20. Consider very small error epsilon equals 10 to the minus 200. Why this number? You can consider other numbers too. Now, distributive typicality tells us for any quantum experiment with observational outcome Z, for 1 minus epsilon most pure states in H0, so when epsilon is 10 to the minus 200, 1 minus epsilon is close to 1. For almost all the pure states in H0, the Born probability of outcome Z, given by the pure state, differs from the ensemble average by at most something close to 3 to the power minus 10 to the power 20, which is close to 0. That's the whole thing I want to show, is that the difference is pretty small. The difference between typical wave function measure on Z to the ensemble average of Z is pretty close by quantify this error term. Now, you say, how can that be true? Well, the high dimension here is relevant for typicality statement. And we are trained, sometimes we train our intuitions by thinking about two-dimensional block space, block sphere, and they're useful, but we have to think about the differences here too. In a two-dimensional Hilbert space, on 2 dimensions, not high, 2 dimensions, H0 equals say C2, such that for a spin half particle with fixed position, 10% of all unit vectors have 90% or greater probability for the outcome up in a Z spin measurement. So you can actually distinguish quantum states using this way by, say, Z spin up outcome. But if you scale up in the Hilbert space that has N tensor product, C2 of M spin half particles with fixed positions and large N, nearly 100% of wave functions have probability near 50% for the outcome up in a Z spin measurement on particle 1. Just like you have entanglement up and down and nearly 50% on up for almost all the wave function. Now the theorem is quite general. When one proves distributive typicality, there are no assumptions about interactions between the subsystem and the environment. There's no need to involve chaos, ergodicity, or mixing. Sometimes they are problematic for foundational reasons. It applies to thermal equilibrium and non-equilibrium. You can apply to equilibrium or non-equilibrium substates as long as substates have tight enough dimensions. It applies to every POVM. But the main theorem of POVMs, the theorem covers every observational outcome arising from arbitrary quantum physical experiment. So this yields a surprisingly strong limitation to knowledge. Okay, let me kind of define 2 more things and give you the core results. Now let's say, what do you mean by distinguishability here for quantum states? Here's one clean sense of distinguishability. And the next sense is to be more defined more precisely. The clean sense is just something that we know about orthogonality conditions, right? But then here, it's like for 2 quantum states, psi 1 and psi 2, we say they're perfectly distinguishable by observing outcome Z equals to Z, say spin up of Z direction. It's only if one wave function assigned this outcome probability 0, another wave function assigned this probability 1, or vice versa. So they're totally destroying probability, one extreme, another extreme. But you can relax this condition to perfect distinguishability in terms of reliable distinguishable by considering close to 0 and close to 1. And you can have how close to 1, close to 0 to be a threshold for the level of reliability. Okay, so let's define more precisely what I mean by reliable test. Let EZ be any POVM and Z any element in Z, any particular element of this set, and delta any positive number. We say that EZ 1 minus delta reliably distinguishes the density matrices rho A, rho B, and here it can be pure state density matrices or mixed state density matrices, doesn't matter. If only if the difference in the trace probability of EZ given by rho A and rho B are going to be greater than or equal to 1 minus delta. So the probabilities are far apart. It's not like they're 0.5 and 0.51. It's like 0.001 and 0.9999, something like this. Note that distinguishing at reliability level 1 minus delta also counts distinguishing in a lower reliability level, because 1 minus delta is greater than anything smaller than this 2. So the previous example of two-dimensional Hilbert space, example 2, suppose you have particular outcome, z spin up. If delta taken to be some level 10%, 20%, 30%, corresponding to reliability 90%, 80%, and 70%, then easy reliably distinguishes respectively 1%, 4%, and 9% of total pairs of wave functions in this Hilbert space. So we're going to show that for fixed delta in high-dimensional Hilbert spaces, the distribution typicality result forces the fraction of pairs that easy reliably distinguishes to drop quickly and become essentially 0. So all this number 1, 4, 9, 16% is going to be essentially 0 when we go to high-dimensional Hilbert space. Now formulate the mathematical basis for Keming. The first corollary concerning reliable distinguishability, there is no reliable distinguishability whatsoever. Let EZ be any P over EM, Z any element in Z, and epsilon greater than 0. Now, if D0 is greater than 4 over epsilon, so if epsilon is 10 to the minus 200, it's going to be 4 times 10 to the power of 200. So that's kind of reasonable assumption about large system size for Hilbert space. Then for 1 minus epsilon most psi A in this, EZ fails to 1 over 2 reliably distinguish rho A from rho B being normalized projection on the subspace. Furthermore, under this condition, then for 1 minus epsilon squared most choices of the pair wave functions, EZ fails to reliably distinguish them with reliability 50%. So the idea is that for any particular chosen experiment outcome Z, and for any two pairs that are typical wave functions, can they be distinguished by this outcome? Well, remember, almost all the wave functions assign nearly the same probability when chosen particular outcome Z. So typical pairs of wave functions will also assign nearly the same probability to this outcome Z. So they cannot be reliably distinguished. That's the key of this theorem, corollary. Warning, you say that cannot be true, but maybe we're thinking about different orders of quantifiers. So it is easy to get confused about order of quantifiers in this statement. Observation typicality, as we've proven just now, has the following form. For n in E and for most psi, something is true of psi E. It is weaker than the statement. For most psi, for n in E, something is true of psi E. So here's one example. Every day, most students are in class versus most students are in class every day. The first one is weaker than the second. The second one implies the first. That's a kind of order of quantifier. For all and for most, they don't commute. So the stronger statement for most psi and for n in E is false in this context. The false but stronger statement corresponds to the following, which we call super strong observation typicality. For most quantum states in high-dimensional Hilbert space H0, for any observation EZ, they cannot be distinguished by EZ. It is false because here's one simple and trivial example. If EZ corresponds to one-dimensional projection on some particular wave function, intervention particular wave function, then the probability of this one equal to 0 to 1 by pure state, whereas the ensemble average assigned is nearly 0 probability. So you can distinguish that from the ensemble average. Okay. The super strong property requires a uniformity in the class of typical quantum states, because you say, think about for most students every day. This means you have a particular class of most students in mind. But for every day, most students, you can have shifting, whoever is missing class, right? So similarly here, you can have observation-dependent typicality classes. But the super strong property requires a uniformity in the class of typical quantum states. Well, observation typicality, which we prove, allows that typicality class depends on the choice of EZ. However, observation typicality, weaker statement, is sufficient for our purposes. Why is that? Observation typicality holds for any chosen experiment. So it is true for the actual experiment, whatever it is, whatever outcome it is, that we happen to perform in an arbitrary time. It covers all possible EZs in any particular chosen POBM. By the way, I want to mention, in the paper we might discuss this somewhere, the stronger statement, even though it's false in general, is actually true for local observations up to half the size of the universe. So canonical typicality corresponding to local observations is true for the strong version. So actually, for most wave functions, for any local observations up to half the degree of freedom of the universe, they cannot be distinguished by that. But for in general observations, local or non-local, the weak version is true and is sufficient for our purposes. Okay, we might try to distinguish. What if we don't insist on high reliability? We might try unreliable tests with distinguishability based on tiny differences in probability, like 1/3 and 2/3, 1/4, 3/4. Maybe that can give us some information. So we can define the favoring ratio in terms of the difference in likelihoods given two wave functions of some particular chosen experiment EZ, outcome EZ. It turns out the favoring ratio typically deviates from 1 by only a negligible amount, such that typical states cannot even be unreliably distinguished. This requires the assumption that the outcome the probability is not too small. So the ensemble average probability for EZ is not too low. They can prove the following result. The likelihood ratio is bounded by some two things. They're very close to 1. So whenever D0 is far greater than epsilon to the power -3, then the favoring ratio for typical periods of quantum states are still very, very close to 1. So even likelihoods don't distinguish that much. Okay, suppose you say, okay, I don't like likelihood either. I want to be a fully Bayesian analysis. I only trust Bayesianism, a probability over typicality or likelihood principles. Okay, so even for the Bayesian, you can do a following Bayesian analysis. Suppose the prior probability distribution over quantum states in the Hilbert space is given by the past hypothesis by the measure mu0, the uniform distribution. You can consider Gaussians too. Let's start with the uniform one for simplicity. We show that for this Bayesian prior, if the observation is not too improbable, doesn't matter what it is, doesn't matter what kind of observation it is. If the observation is not too improbable, the posterior probability distribution is very close to the prior. There's one version, there's another version that makes it even more precise. But suppose the conditions hold with dimension and small epsilon, and also the probability of observation is not too low, then given Bayesian updating, the posterior probability density is almost 1 for almost all wave functions in H0. And this also entails for any set of wave function in Hilbert space, the posterior distribution on that is very close to the prior. This follows from integration theory. Okay, the previous results apply directly to orthogonal quantum mechanics, Copenhagen interpretations, and so on. Also applicable in Bowman mechanics, Girardi-Rimini-Weber class theories, and averaging quantum mechanics. So let's think about Bowman case in more detail. Here's a key fact in Bowman case that follows from the previous results we mentioned. For any subset omega in configuration space, the probability of the event actual configuration is in omega, which is an integration over some form distribution over configuration states, is nearly independent of psi T0 for typical psi T0 in the initial subspace. Now, why do we focus on omega and distribution over omega? Well, here's the necessary condition. We can hold if the event is known to inhabitants of a Bowman universe at time t, then it is of the form Qt is in omega for some subset t, omega. So if you have some knowledge in the form of pointer readings or ink recordings or records, or at least it can be, in David Albert's words, parlayed into this kind of position form, then they're subject to the same result, which is that in Bowman universe, no observation at any time can reliably distinguish between a typical wave function from the ensemble average or between two typical state vectors. The conclusion covers every possible observation or experiment in the Bowman universe. Observational outcomes be recorded in the configuration of some particles or pointer readings. Actually, you can even use the condition just they can be at least published in some kind of finding journal or something. Another result also covers situations where you make consecutive experiment observations over time, since the outcomes will be recorded and thus can be read off from Qt at some particular time when you publish the results. We can also make an argument for the impossibility of unreliable distinguishability if the outcome is not too unlikely. On the other hand, the precise microtrajectories of all Bowman particles may contain more information about the initial wave function. Chua and collaborators proved already that observers inside the Bowman universe cannot measure a position several times without introducing decoherence and changing the trajectory. And therefore, Bowman observers in the Bowman universe run by Bowman laws in quantum equilibrium do not have access to the full trajectories, and the observation results just derived remains valid. Consider next a collapse theory, GWF. It's a GWT with a flash ontology in spacetime. A flash is the center of a collapse. A collapse with a center here, that constitute the galaxies of tables and chairs. So here's a key result that one can derive for GWF, and that follows from observation typicality, is that for any subset M in the space of possible histories of flashes, the probability of the event Ft in M is nearly independent of psi T0, or typical of psi T0 in the subspace. And it's followed by taking the P of M e to the P of M governing to a distribution of all flashes. Why is this relevant? Well, if an event is known to inhabitants GWF in the universe and time t, then it is of the form of some flash distribution, for some time set F. Okay, so this suggests that in a GWF universe, even the exact pattern of all flashes, of all space-time, from Big Bang to the end of the universe, will not reliably distinguish typical wave function from normalized projection or from another typical initial wave function. The conclusion covers every possible observation or experiment in a GWF universe, because they will be recording some of the flashes, or can be at least recording some of the flashes. We also make argument for the impossibility of unreliable distinguishability under certain conditions. The difference from the Bowman case is this. In some sense, the GW constraint on knowledge is even more severe than the Bowman case. The exact history of the universal configuration in quantum mechanics may provide sufficient information to determine psi T0 up to some equivalence class, maybe. Whereas in GWF, even the exact history of all flashes, all the primitive ontology, all the local variables, all spacetimes, is of no help. Thus, GWF provides, in a sense, a stronger kind of limitation of knowledge of quantum mechanics. Now, inhabitants of a GWF universe living at time t may very well find out a lot about psi t, know that this doesn't give information about psi T0. Okay, let me explore some philosophical implications of our results in brief. And many things we can discuss, maybe it could come out in Q&A. So here are 5. Okay, first, limitation to knowledge. Observation typicality places severe limitation to knowledge in the quantum universe. In a large universe, if we don't know what a quantum state is, no experiment can distinguish the whole majority of universe quantum states. This is in principle limitation that cannot be overcome by new technologies. In Bayesian, if the observation is not too unlikely, they cannot learn enough about quantum state. The limitation is derived from the laws of quantum mechanics. This itself is a derived law of quantum mechanics. And in future work, we want to think about how this relates to current work about quantum tomography and quantum computing. There is this recent strand of thinking that not only can we learn reconstruct the wave function of small systems, but perhaps with the help of machine learning and AI, we can actually kind of scale up this process to gain knowledge about bigger systems, maybe the universe. So Robert Huang's dissertation on quantum learning is quantum learning in the quantum universe, right? And the Huang kind of practical program is to try to find efficient ways to estimate and test and measure the quantum state, even for larger systems. So the ambition there, I think, is to have ways of gain knowledge of quantum state for bigger systems, but also typicality and that are prima facie intention. So we want to be careful about how exactly is that compatible or maybe limited by observation typicality. What kind of things can we say even for experiments in the lab or quantum computers, 100 qubits? On the flip side, and maybe this is also in kind of in harmony with existing knowledge, is that even though we have proven something about limitation to knowledge about precise pure state, that there is a kind of gaining of knowledge somehow. The flip side is that concerning the observable properties in the quantum state, and actually any property of quantum state, any observation, we know a lot about them because of typicality results. Assuming our universe typical amount will satisfy the past hypothesis, even though we do not know which one it is exactly, which pure state is exactly in the ensemble, we know that there's uniformity in the probabilistic predictions. Almost all of them predicting any predict-chosen experiment with nearly the same probability. They are very nearly the same as the probability prediction of normalized projection. The precise choice of a typical pure state makes almost no difference to prediction. Fixing the initial subspace nearly entirely fixes the probabilistic predictions of typical quantum states with only a small error. And a small error doesn't make a difference in terms of extreme variations. Okay, the second And the third one is more philosophical and epistemological and methodological. Remember, there was a time when philosophers really liked positivism, and scientists too. Maybe still it's more fashionable in science and philosophy. Roughly speaking, positivism is the statement that the statement is unscientific or meaningless if it cannot be tested experimentally, and the variable is not well defined if it cannot be measured. But in quantum mechanics, there's an irony here, because psi is an objective feature of the universe, a well-defined variable of the theory. It guides particles, collapses, or realizes the emergent multiverse. It is as central as it gets to things in the physical theory. Observation typicality suggests that psi is undetermined by observations and cannot be measured even imprecisely. We know that many things cannot be measured precisely, but even imprecise, narrowing down the choices, narrowing down possibilities is impossible in some cases. So this suggests that positivism cannot be true if one takes a realist attitude towards quantum mechanics, and undermines this spirit even more, that many things are scientific, meaningful, and well-defined, even if they cannot be learned, they cannot be empirically discovered. Okay, 4, on the initial quantum state, so psi is an objective feature of the universe and well-defined variable in the theory. Often question, what does the wave function represent in the physical universe? Is it a table? Is it a chair? Of course not. It is much more abstract and global. There are two main approaches to the wave function. One, psi is ontake, something in the world, part of the furniture of the universe. And second is psi is gnomic, more like law of nature. Now, the first view says psi is a physical thing, like a physical field, that exists as part of the building blocks of the universe. And 2 says psi is a physical law, like Hamiltonian function in classical mechanics, that tells physical things such as particles and fields how to move, dance around in space-time. Observation typicality perhaps less surprising if psi is a physical law instead of a physical thing. For physical thing, there should be no principal limitation on how much you can measure this. Very precise measurement is difficult, but why should imprecise measurement be impossible? But if something is a physical law, determination comes naturally with physical laws, gnomic things in nature. So maybe it's less surprising if psi is gnomic than ontake. Last, okay, density image realism. So this is the position that I'm trying to develop and defend and engage in the literature on the quantum state being objective, but it can be a mixed state. The particular theory being suggesting is the one calculus account. The initial quantum state of the universe is ρ0, normalized projection, onto the Pascal subspace. Observation typicality makes clear another reason to consider density image realism and the one calculus is that if typical pure states psi T0 compatible with Pascal policy do not lead to different predictions that are so different, why not just use the density images instead? Because nearly all the pure states make nearly the same predictions as ρ0 for any particular thing experiment. After all, ρ0 may be regarded as much simpler than any typical psi T0, even though they're nearly predictably equivalent. Okay, let me conclude, and my time is almost up. We have shown that the central object in quantum theory, the quantum state of the universe, is hidden from observation if it is typical. How do you generalize this to subsystems and open system is something we leave for future work. It is, we think, the strongest known result about limitation to knowledge in the quantum universe. Perhaps the strongest such result in physics, because we don't see something like this in classical general relativity or classical mechanics. The variables and things can be learned, even though the amount of determination is not so severe in the sense you cannot learn anything about them. Assuming the universe we inhabit is typical in H0, all data alone will tell us very little about exactly which one it is that we inhabit. Nature, it seems, is far more secretive than we have realized. Okay, the end. Thank you for your attention.
I mean, for experiment, I'm measuring some macro parameter here. Let spatial values, deviation spatial values, universes.
Yeah, sure. So we measure some parameter of the early universe. Let it be deviation from spatial flatness. We know the universe is nearly flat, but we measure it. As it happens, we find some very small deviation from flatness. Now, the normal way I'm not a great fan of the past hypothesis way of setting up quantum cosmology, but let's assume it. The normal way that would work is I'm going to have a bunch of macrostates, and what I've learned by that measurement is which macrostate I'm in. And that seems to be substantive knowledge, information I've learned by measuring quantum state. Now, if I think about the early quantum mechanics, then of course it's the case that if I've got a Hilbert space or in my quantum cosmology, of states with one curvature and another Hilbert space, another subspace of states with a different curvature. Of course, it's true if I take the tensor product of those two, or the sum of those two spaces, the overwhelming majority of states in that space will actually be appropriately weighted superpositions. Of course, that's right.
Yeah.
But by the past hypothesis itself,
Yeah.
I'm not assuming something like that. I'm actually assuming as a theoretical assumption that the quantum state is chosen from this highly atypical, from one or other of these highly atypical subspaces of the overall space there. So, I mean, that seems to be a substantive way in which I am gaining material information about the quantum state through measurement. And part of the worry I have coming from examples of this kind is the way the quantum version of the past hypothesis machinery is set up. We're kind of taking as a starting assumption the quantum state lies in a definite macrostate, which is relatively close to saying that it's already assumed to be one of a number of states that are macro indistinguishable by the definition of macrostates. So I don't have a kind of gotcha to come from all of that. I just want to put that out there and invite you to comment how that kind of stuff fits into the framework.
Yeah, that's a great question. So everything is that I think is compatible with the result in the sense that suppose you have several subsets to choose from. What is the right version of the past hypothesis? That can be somewhat empirical, somewhat theoretical. And that question is not touched on by this result. There will be a very generalization open question, which we're still thinking about, which is, is there a version of this for typical subspaces too? And how to generalize this from thinking about typical states to typical spaces in Hilbert space? But of course, there's going to be type of questions. How do you resolve that? Second question is that I think that's is very much consistent with what you said, is that we can learn a lot about our initial macro state. And that on this picture is not getting knowledge of condition on the macro state. What is the pure state it is? But this result is more like, suppose here is the correct law, whether it's partial version of past hypothesis it is, and correct typicality measure distribution on this subspace. Then can we do some experiment here and make some observations here to learn which one it is, the pure state? And this places limitation on that kind of knowledge. But this is in the same kind of conceptual game as thinking about general relativity. Suppose we fix the laws of nature and allow ourselves to inductively learn anything, have any kind of observation. Can we pin down the global structure or some kind of other things within that theory? And the answer here is no, given under the conditions.
Yeah, I guess I'm just worried that that was sort of built into our notion of macrostate, microstate anyway. We were never, I mean, this isn't to detract from the sort of wider generality and power of the mathematical results we're using, but it was sort of generally built into the idea of things like equilibrium, that one's measurements would tell us macro parameters, but one didn't expect access to the micro parameters. So I'm just wondering, I mean, whether the epistemic situation is actually that different from what we thought from classical statistical mechanics.
I think that for classical mechanics, like a coin toss experiment, we can learn by doing, is it tails or heads, and get knowledge about the initial phase point. And suppose we condition on that we do experiment in this particular setup, then okay, this result have initial points.
Yeah.
And the Bayesian can learn a lot too by just doing normal experiment too. But that kind of thing will not be possible in the quantum case. So you have a Hilbert space subspace, you have some distributions, and no observation can reliably distinguish among the initial substates.
That makes
so
sense.
that's different.
That sounds fair. So I take it, I'll finish after this. I take it if I had an epistemic reading of quantum states, I wouldn't think there was anything strikingly different here. I have to be assuming some of the background, which you and I share, that would drive us to sort of onto quantum readings.
Yeah, that's a good question. I was thinking about the same question earlier, like a few weeks ago. I was asking someone at who does engage with quantum Bayesianism, quantum epistemic views. I'm not sure because there are motivation to consider tomography and quantum information kind of programs for reconstructing wave function, even for epistemic approaches. And you can apply this to a 100-qubit quantum computer and trying to say, okay, can we do some experiment, single shot, one observation about the system, such that we can learn something about the quantum state? And if it is very small subspace, yes. But if it's a large subspace, you have a kind of uncertainty over many dimensions, then it's no longer possible. So I'm trying to understand, is that going to be engaging with some of the ambitions of tomography for the wave function?
I better pass on. I'd have to follow that. Okay, thanks. There must be other people in the line.
So, yeah, it's possible.
Cool. So something you mentioned at various points is, yeah. So something you've mentioned at various points is it's kind of possible worlds way of thinking about things. And really, I was just curious if you have, if this is just meant to be kind of instructive intuition building, or there are some kind of formal constraints you can point to there, and in particular, whether you can kind of trace that disagreement or difference between the two perspectives to some kind of formal conditions within modal logic or similar.
Oh, it's a good question. Might be epistemic modal logic of some sort that you might naturally tag on to some kind of modal structures of possible worlds. But something like if one has a model, a space of possibilities, and presuming it's natural to assume you can gain knowledge that contracting the space of possibilities, contracting by some reliability standard or Bayesian way. And this will be limitation on that kind of contraction and gaining knowledge.
Yeah,
okay. For example, in a classical universe, when I open my eyes, I see there are people in front of me. This rules out many, many worlds, such that it rules out them. They can like distinguish between them, right? But if I open my eye in quantum case, it doesn't rule out any wave function, and moreover, it doesn't distinguish reliably to be called pairs of wave.
Okay, cool. Yeah, let's talk more.
Sorry.
Thank you. This is very interesting, lovely result. I really like it a lot. I have a comment about the Bayesian and stuff, which actually is, or the qubit stuff, which is actually relevant to something I want to say. So when in your response to David, you talked about tomography and qubits and learning about the quantum state. I spent much time talking to Chris Fuchs, and I sort of heard him squealing in pain when you said, learn about the quantum state, because that a qubist should never ever say. What the cubists do say about tomography is that what we call learning about the quantum state, like you're doing lots and lots of repetitions of experiments on systems prepared in the same way, is for quantum Bayesians a convergence result that they'll converge to assigning closer and closer to the same quantum state in the sense of their probabilities for the next experiment will get closer and closer and closer. And I think that there's an interesting distinction about the two ways of thinking about what it means to learn about the quantum state that I think is relevant to your work. So, imagine you hand me some system with a high dimensional Hilbert space, and you say, I prepared this with a randomly selected pure state. I get to do experiments on it, then I have to guess what it is. Okay, so let's say I can do a, ideal von Neumann projection valued measurement, and I get a result, and I say, okay, I got this result, and I conclude about your pure state. It was not in the subspace orthogonal to that result, and you say, yeah, you didn't learn very much because that's tiny, 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 right? And that's true, right? And there's a sense in which I didn't learn very much because I didn't exclude very much. And something similar would be said about the reliability things. But there's a sense in which I learned a lot if there's a limited number of macro variables that I'm interested in predicting. It is possible that as a result of that experiment, my ability to, the probabilities for future experiments have actually changed a lot, right? And so I think it would be good to think about some way to quantify learning in terms of, you're not trying to figure out what state was prepared, but how valuable was this information, macro information, for future things that I might care about? And David mentioned, there might be a limited number of macro variables that I'm interested in that could be compatible with a huge dimension of pure quantum states in the Earth space. But there might be, like, in one sense, I didn't learn very much, but there might be another sense in which we actually do learn a lot.
Right. So I think the learning will be now, given this result and given the conditions, it will be about the different subspaces, different density matrices, different probability distributions. But there's a way that some people talk that we have a Bayesian way of thinking about everything, a probability distribution over many states, and that gets changed. The prior starts to evolve to some posterior, and the differences kind of give you a measure of how much you have learned. And if the posterior doesn't differ that much from the prior, then there cannot be such differences in learning. Or there's somewhat dramatic learning. So I'm trying to figure out exactly which claim to engage in the literature about learning. Because one thing that I've been puzzled about is that if the quantum state initially is density matrix over many dimensions, then you don't get knowledge about density matrix that much. They can predict almost anything, or actually anything from the Eugene density matrix without doing experiment. The predictive accuracy for that observation will be the same, whether or not you do the experiment here, because it doesn't change the prior distribution that much.
Michelle? Yeah, okay. Well, thank you very much. I was wondering about the same issues that Wayne was raising, because I'm not convinced that there is such a radical difference between learning in classical theories and in quantum theories. Like you said, if you do a coin toss, then after the result of that toss is known, then you can say, oh, I have restricted my knowledge to a particular subset in phase space. And similarly in quantum mechanics, regardless of what the dimension of your Hilbert space is, you can do, you have observables, say like the energy, and you can measure the energy to lie in a certain interval. And by that means you will have gained knowledge about a particular subspace of Hilbert space in which your state must lie. So there's a complete analogy between classical and statistical, classical and quantum learning on that level. And much of the difference in which you have claimed to exist between classical and quantum learning lies into going to these higher dimensions. And my question or my argument might be that if that's so, then you can do the same game in classical statistical mechanics or just coin tossing. And in fact, I would say the whole formalism you have been using. So there's a Hilbert space, there are observables in the form of POVMs, etc., etc. That formalism is so general that it doesn't really distinguish between classical and quantum systems. I mean, the only thing I need to add to talk about the classical universe is to say that all my POVMs commute. And then I'm dealing with a classical system. So if your results are valid for quantum systems, they're valid for classical systems as well.
Well, they are
And really, if you go to higher dimensions in coin tossing, this would go to extremely long sequences of coin tossing. And then you have concentration theorems for the probability measures, which are exactly alike the ones you've been talking about. And so I think you would also find exactly the same results or analogous results for the probabilities of learning there.
I think there are no analogous results like this for the classical learning case, because we know that in a high dimensional phase space, doing a coin toss experiment rules out half points. So the posterior, the prior, would be very different from the posterior.
Yes, but you have now probability measures over enormously long sequences rather than just heads or tails.
But even in enormous sequences,
David first.
Well, I mean, in partial defense of Eddy's position here. I mean, I think the level of the analogy, which I think almost certainly is right on a formal level, would be between learning about the prior classical probability distribution through measurements versus learning about the quantum state through measurements. But then the question is, at the interpretational level, do we want to analogize learning about quantum states to learning about classical probability distributions, or learning about underlying classical microstates? And that's going to depend on how you think about the measurement problem. I think that goes back to my suggestion that on an epistemic reading of quantum states, these situations are quite parallel.
Yeah, so one might ask, that's a question which you mentioned, is can we prove a similar theorem about probability distributions? Typical probability distribution might have similar property, I think that's probably true. But typical classical states don't have this property, and learning about classical states, we don't have this limitation to knowledge.
I would say microstate, just to make it completely explicit what you mean here. Yeah.
Yeah, I was going to say something very similar. So, if I go to the classical case, as you said, the only difference is all our POVMs commute. The big difference between classical and quantum is that in classical, distinct pure states are distinguishable, and in quantum they're not. But so as Dave said, the analog is going to be over classical probability distributions, but then the classical analog of a quantum state is a classical probability distribution, not a classical pure state.
Right. Yeah.
Yeah, hi. Thanks for a very nice talk. I think the result's very nice. I think my question is more of to understand the scenario exactly. I think there was some chatter about this already. So this is a single shot situation whereby, and for a particular member of the POVM, is that what the claim? That if whether such a member of the POVM exists for the states in the Hilbert space, like how would you? It's a single shot thing. It's not a tomography thing, right?
So so it's not about the POVM existing or not.
Okay.
So suppose you observe some outcome, they point about some direction, some kind of ink recording, some kind of records, whatever it is, the outcome, and does it give you information to reconstruct, to learn the quantum state? And quantum state in the high-dimensional Hilbert space that is typical or some property distribution. And the answer is no under the conditions. But in tomography, there's we do many copies.
Yeah.
And can you learn something from distributions, frequencies? It's a great question. So when I mentioned distribution typicality, you may be wondering where is distribution? Because single probability number, right? So you can generalize this distribution typicality to distribution by just taking the intersection of various POVM elements. So instead of taking, a single EZ, consider a distribution over several EZs forming the POVM. And let's call this thing L, L being the number of EZs in this. And the bound is no longer 1 over this, but L over this. So L contributes to how large the area is. Now, if the bottom is very big, doesn't matter how large L is, microscopic experiment or realistic experiment, 1,000, 1,000,000 outcomes will not make a difference because the bottom is going to be very large. But when you go to bigger or smaller dimensions, or smaller systems, the trade-off becomes visible. And the question is, how important is that for tomography? And there are related results tomography researchers have pointed to, but I don't think it's this one. So that makes us wonder, perhaps you're wondering too, does this place limitation to tomography? How efficient can this be?
I vaguely remember some result that, so typically for these informationally complete tomography POVM sets, I think they usually go for these mutually unbiased bases. So for qubits, that will be like the Paulite basis, right? And I might be butchering it, but I think it's well known that nobody can find like beyond 7, like the dimensionality of 7. Beyond that, I mean, besides like certain multiples of primes that are already known. And then I think this might be wrong, but I remember vaguely that some people are quite sure that these don't even exist on higher dimensions. So if I can find the paper, I'll
Please
let you
do.
know.
That'll be very
Yeah,
useful. Thank you.
thanks.
Back to David. Okay. I mean, let me follow up your quick comment about the Wentaculus. So, I mean, I haven't proved this in my head, but I bet a lot of money that your equation 2 generalizes to mixed states. As in, if I pick a random mixed state with respect to the trace norm measure on all the mixed states on that space, I would be astounded if there isn't some analogous result that it's extremely close in expectation value to rho 0. So it feels like just as no empirical information is going to tell us which pure state we have, then no empirical information is going to tell us which mixed state we have. So in the light of that, can you say a bit more about why the Wentaculus is actively advantaged by this set of results?
Yeah, it's a good question. I mean, that kind of analysis result is exactly what got us started to think about this question and realize that it applies to pure states and give us a very clear target too. But for the Wentaculus idea, it's kind of more theoretical argument that suppose you think that the some kind of simple law specify initial subspace, macroscopic state, without specifying the initial microstates, then there's kind of a simplicity argument for normalized projection. But of course, if there's a even stronger argument for particular pure state being very simple, then of course that would be another argument to consider.
Good,
but here's like considering suppose there is no good argument for any particular pure state in the pH subspace, and there is going to be normalized projection be a natural canonical for the subspace. Then this one and pure state is going to be making similar predictions. So
good. Okay, good. So if I've got if my hypothesized cosmology returns me a subspace of possible indistinguishable states, you're saying in that circumstance there might well be, and returns nothing more, there might well be a simplicity argument for the Wentaculus. If my hypothesized cosmology, returns me a particular state, but of course there's a subspace of states that are indistinguishable to it, it wouldn't be that this argument would support the Wentaculus over that region rather than just supporting the initial state.
Yeah. So you can have an argument that, I mean, the upshot of this is that the learning with knowledge about the quantum state, the universe, or big system is quite theoretical. If we have theoretical reasons and empirical reasons together, depending on a unique pure state, that's great. I'll be very happy to.
Great. Okay, that's what I thought.
Thank you.
That sounds good. Only no one else. Okay. Well, let me think. I've had 2 days, so
This is just sort of a minor comment. It's not your central point. Like you had a slide about implications for positivism, and it was incompatibility between positivism and this result on the assumption that the quantum state is an objective fact about the world. Typically, if someone's motivated by positivism, the idea is that the observational vocabulary is to be taken literally, and the theoretical apparatus is basically not supposed to be referring to anything in the world, but a way of systematizing our observations. So if I were motivated by positivism in the first place, I wouldn't be taking the quantum state to be something part of the furniture of the world. And you see that in the early days of discussions of quantum mechanics. So you have people explicitly invoking positivist motivations for saying the quantum state is purely symbolic, or it's a representation of our knowledge and not a fact about the world.
Right. It's good point. I think that it's for those who are more, accepting the reality quantum state, then this one has spike. But then those people might be half-hearted positivists, because I've encountered people in physics conferences that say quantum state is real. They accept it because of entanglement, variability, inequality, and so on. But they think that anything that's untestable or unlearnable is not scientific. I said, what about quantum state itself? I said, well, maybe the quantum theory is non-scientific or something. They have 2 models told us that. But I think you're right that the hardcore positivists will be much more inclined to epistemic views about quantum state.
So this is a rather different line. You mentioned as an advantage of this result that, or one of the features of the result, that there were no contestable assumptions of ergodicity or mixing or chaos or all these kind of dynamical assumptions. And I wonder if that's really comparing like with like. I mean, the typical, so to speak, cases when we use assumptions like that are something like, I've got a system that's equilibrated in isolation. So maybe I had a gas initially confined to one half of the box, I pull out the partition, and then I allow the system to evolve adiabatically. Now, in that situation, we know, let's stipulate the system has entered or is extremely likely to have entered the macro state of corresponding to the gas being uniformly distributed. And we know that typical macrostates in that region have the sort of characteristic features, and that with overwhelming high probability, if you make a measurement on a typical state, will return the same kind of results. But of course, the state the system is in after equilibrating is definitely highly atypical, precisely because it's known to have evolved from this very small subspace. And then translated into typicality talk, all of these ideas of ergodicity or mixing or whatever are all there to say why, despite the fact that in this relevant sense the state is atypical, nonetheless it's indistinguishable from typical states. And your machinery in itself, I take it, is silent on that point, because all these results presuppose typicality, so they won't say anything about an extremely atypical probability measure over the post-equilibration Hilbert space. So this isn't an objection to the core results, it's just a concern that that kind of comparison set is kind of comparing to results that are aiming at a somewhat different result, which is to justify certain features of the post-equilibrated system rather than the initial past hypothesis type system.
Oh, I see. I had in mind some kind of the approach equilibrium results using ergodicity and mixing, which are not really about after equilibration. But I take your point that some people use those results to justify the typicality measure, but not here. The typicality measure is here chosen as a fixed part of the physical theory, probability distribution, typicality distribution. We can talk interchangeably between typicality and probability here. And I mean, this is not kind of a bias. You have talking in this way, because the Bayesian results kind of analog to typicality result here. They're almost equivalent mathematically.
Right, but if I run the sort of hard line mixing ergodicity type theorist, applying their ideas to the past hypothesis, they're going to say something. Well, there's a class of position here which would say something like this: that the reason we should assume that the state is typical on the, or has these features in the past hypothesis, because even the past hypothesis is dynamical, and letting it evolve a bit is bound because of the mixing dynamics or whatever. Letting it evolve a bit is pretty much bound to end up one of these states that has these features. And you want to say, sure, but typical states have these features anyway. And if they really want to sort of thump the table on this, they can say, well, who says anything about typicality? We should assume nothing about the initial state. Nothing at all, and nonetheless we should be getting these things. I'm not sure that's very defensible, but that would be the point of engagement there.
That's interesting. Yeah, I was assuming that the typicality approach will want to prove a version of second law with typicality measure kind of fixed by the theory, and then try to see that something holds for typical initial points. But in light of this result, they can prove something weaker, not from nothing, but from something like, if some property that can be observed that has some kind of consequence physically is true for many points, then it is true for most points.
But that's not exactly going to. I mean, it won't solve the problem by itself. I mean, again, if you want to understand equilibration in this framework, it's consistent with everything you're saying, that the actual states of the expanding gas make their way neatly into a picture of Mickey Mouse and stay that way forever.
Right.
So there has to be some dynamics involved in explaining why, once the gas on the left-hand side of the system evolves to fill the whole system, any measurement I make of it is going to correspond to measurements on the canonical state. That isn't something you're ever going to be able to get out just by these Hilbert space kinematics.
Right. Justification for the measure might depend on the laws, dynamical laws, how it evolves. Yes, I think you're right.
Yeah, I just had a quick clarification about the positivist stuff, because I take it that on standard kind of positivist views, what they're going to say something like, it's in principle empirically testable or observable or something like that. But then it looks like there are some limitations that you put on what counts as the kind of observations that we can make. But I don't think positivism comes with those limitations. It could be really, you could do things well beyond what we're imagining any human could observe, like go back in time and things like that. So I was wondering if those two ways of understanding, in principle, empirically observable, actually match up. Yeah. So that's
Okay,
it.
yeah. There might be different versions of positivism, but I was thinking this will be compatible with a very strong version. There's any in principle nominally allowed kind of experiment with records, right? So you have any kind of, in quantum mechanics we represent measurement outcomes by this POBM elements. So if something covers any POBM element, any POBM, then this covers automatically all the quantum mechanical allowed observations. So this, I think, fit in the box of in principle observations. There are weaker versions or stronger versions sometimes if you restrict class of observations. But this result applied to reliable distinguishability applies to any observation. However likely it is, however global it is, fine-grained it is, whether we can do it or not, right now it is in principle observation. Thank you for the question.